Alrighty. Okay. Well, it is getting to be the end of the semester, so I just want to give kind of an update on where we're at. So of course, there's the design report due today. So just make sure you're remembering that. There's a spot now, I hadn't had one, but there's a spot now to turn your final report in. Just the note here, I have, make sure to turn in your Excel model, like your spreadsheet, or I guess if you made it in Google Drive. Google Drive, you can save it as an Excel file. So turn in an Excel file of your model, mainly because if you come in your report and you have really wackadoo things that you're trying to recommend, and I can go back and see from your model, oh, it's because they made this error in their calculations and that's why they're recommending that. So I can go and kind of cross-check that if need be. Primarily, I'm not going to be looking at it unless needed. But it is there. It will be helpful to get extra credit if you did have mistakes of some kind in the model that are leading you to make strange recommendations. The other thing to take note of at this point, the two other things. Thing one is exam number 3. So that's going to be on Monday, next week, Monday. Exam number 3 is going to cover stuff that we covered in chapter 6 and chapter 8. So that was Bernoulli's equation and head loss type stuff. So stuff that you guys now have been sitting with and playing with for quite some time in the report. I'll put together kind of a more detailed outline of what's actually going to be there so that you have that to go off of, but it's going to be really chapter 6 and 8. The other thing is homework number 10. So this will be our last homework set. It will be due Friday the 7th, which is the last day of classes, because we're getting that close to the last day of classes, which is a happy thought. Or maybe a sad thought, but at least it will be done, right? So Friday the 7th, that's a week from Friday. Obviously, we have an exam before then, so I'm not necessarily saying, like, here's the homework assignment, make sure to work on this right now, because we have an exam to work toward. But I wanted to give this to you early because you'll be able to start on this and you could finish this really after today's class. So you have enough stuff, you'll be able to finish it kind of whenever. And also because there are a couple problems on this assignment. There are a lot of problems on this assignment that are like watching videos and answering questions about it. And 3 of those, so there are 3 like textbook problems and then 2 video problems. So I want to give you like time to actually be able to pull those up and spend a little bit of time with those. But also there are 3 that are possible for extra credit. So you can complete all 3 of these for a total of 6 points extra credit. So if you have some extra time over the next week and say you want to do 1 or 2 of these this week instead of saving it all for next week, gives you a little bit of flexibility given your schedule and what you want to be working on. The extra credit ones especially are things that we haven't really talked about in class and we won't really talk in depth about in class, but interesting concepts or ideas that maybe you'll run across somewhere outside of this class in fluids at some other time. So just things that I think it's interesting to be aware of, even if there's stuff that we're not going to cover in like mathematical detail, stuff that it's worth seeing. Yeah, so that's, I think, all of the announcement-y type stuff. Are there any questions on any of that? Feeling good? Ready for the end of things? Feel like yes? Okay. Feel like we all are, but it's coming. Okay, we're going to pick up today with where we left off last time on Friday. So I want to first refresh our memories of what exactly that was. We were looking at, in really kind of this whole section, we're looking at how do we take, fluids is confusing sometimes and complicated and sometimes counterintuitive. So how do we take model systems and use model systems to represent reality? And how do we do that the best way that we can? So we looked first at this idea of dimensionless groups, where we can kind of match the physics between a real system and a model system using dimensionless groups. Essentially, what we're trying to do is we're trying to take all of the different things that are important in a system and boil it down into the minimum amount of groups of things that are actually important. So we went through and we started going through this last time, looking at drag force on a sphere. And this is all stuff that we did last time. So if you didn't do this, look back at the previous video. We looked at drag force on a sphere. We said, well, that depends on the size of the sphere, diameter, it depends on velocity, density, viscosity. So those 5 things should be somehow related, but it's hard to be able to capture what that relationship is because it would be a lot of things. It'd be a lot of experiments to try to vary each one of those things and see how they depend on each other, how they relate to each other. So we're going to boil it down to the minimum number of things and get to something like this, a dimensionless relationship between one thing and another thing or another couple things, and try to get out as many of the extraneous, like extra stuff that we can. So we did this, we started this steps 1 through 4 last time, where first we listed all the parameters. Okay, we have 5 of them: drag force, diameter, velocity, density, viscosity. We listed them in terms of their primary dimensions, like length and time and mass. And then we chose 3 of them, which together we chose diameter, density, velocity, where together these 3 have all of our dimensions, like mass and length and time. They represent all of our dimensions. So we have these 3, D, rho, and V. And what we want to do is now kind of take our 5 parameters, drag force, viscosity, and D, rho, and V, and we want to combine them in different ways that make the most sense. And we'll explain in the next step what exactly that means. We determined in step 4, we had only 2 dimensionless groups. So we should have 1 dimensionless thing, which is a function of another dimensionless thing. So now we're going to say, what exactly are those dimensionless groups? Okay, so we went through step 1 through 4. Now in step 5, we're going to ask, then this is the last step of the Buckingham Pi theorem. Yikes. Okay, in step 5, we're going to combine, again, I think it will be easier once we do this, but we'll combine the repeating parameters from step 3 with the other parameters to make dimensionless groups. So we identified these 3, what we call repeating parameters. We did density, velocity, diameter. We're going to combine those 3 strategically with the other 2 to make dimensionless groups. Right, so step 1 of this, or step kind of 5A, we're going to find what we call our first dimensionless group, or pi 1. Okay, so in this case, we're going to combine rho, v, and d with our drag force. To make a dimensionless group. Okay, so what we're trying to do is combine these four things together so that all the units cancel out, or all the dimensions cancel out. So our dimensionless group is going to be the combination of all four of these things: rho raised to some power, we don't know what that is yet; velocity raised to a power, raised to the b power; diameter raised to the c power, and all kind of arbitrary things that we don't know yet, we'll figure it out, times F drag. So we want this to be dimensionless. So we're going to choose strategically values of A, B, and C so that all the units cancel out. So let's look how that would work. So for density, we have dimensions of mass per length cubed. So we're taking those dimensions raised to the A power. Velocity, we have length per time. So we raised that to the B power. And then diameter, that has units of length raised to the C power. And drag force has units or dimensions of mass, length per time squared. And for this to be dimensionless, that means that our final units are mass to the 0 power, length to the 0 power, time to the 0 power. Everything's raised to the 0 power, so they're all 1. So what we need to do is choose values of A, B, and C to make this true. Right. So in all of these cases, we're multiplying these different factors together. So that's going to be, right, like m to the a times m is equal to m to the a plus 1. Right. So when we have multiplied things, the exponents are going to add. So we can make equations that are, we want this to equal m to the 0. So we can make equations that are like this. So we make an equation for m. So a plus 1 must be equal to 0. Right, so we need to choose A so that that's true, because that will cancel out the mass part of F drag. You see how that works? Then for the length term, so the first term we have, like this term, we have a length to the -3 to the A power. So that would be minus 3A would be that first term. And then we have a length to the 1 power to the B, so that's plus B plus C. We have length to the C plus 1. That also has to equal 0, because again, we want all of these to cancel out. And then the last one is for time. So there's no time in the first term. There is time in the second term minus B. And then time in the last term minus 2. is equal to 0. So now we have to solve these three equations, which a couple of them are fairly straightforward. So we can solve for A. What does A have to be? A equals -1. And we can solve quite easily for B and with the last equation. So negative B minus 2 equals 0. So that means B equals -2. So B equals -2, A equals -1. And then we can solve the middle equation to find C. So this equation now is -3 times -1 plus -2 plus C plus 1 is equal to 0, which is 3 minus 2 plus C plus 1 equals 0, or C equals -2. Okay, so those are our three exponents. So if we choose exponents of those values, then all of the units will cancel each other out and we get to a dimensionless thing. So our first parameter, pi1, is equal to density to the -1, velocity to the -2, diameter to the -2, F drag. Or we can rewrite that as pi1 equals F drag divided by rho velocity squared d squared. So that's one of our dimensionless groups. Again, we're kind of taking these, combining them with our other stuff to get things that make sense. Now, the cool thing about this is we no longer are really going to be talking about how does the drag force depend on all of these things. We're going to be talking about how does this grouping of things depend on another grouping of things. The second grouping of things is our second dimensionless group. So we're going to take pi2. We're going to do the same thing. So we'll use our other parameter mu. And we'll combine mu with rho, v, and d, and make that cancel out all the units for that. So for pi2, again, we do the same thing. So rho to the d plus velocity to the e plus diameter to the f times mu. And we're going to choose d, e, and f so that all the units cancel each other out, or all the dimensions cancel each other out. So in this case, we have mass per length cubed to the d. We have length per time to the e, and we have length to the f. And our dimensions on viscosity are mass per length time. And again, we want to choose this so that it's mass to the 0, length to the 0, time to the 0. So we'll make our set of equations. Again, first looking at the exponents on mass. So mass, we have d plus 0e plus 0f plus 1 is equal to 0. We have an equation around L, so that's minus 3d plus e plus f minus 1 is equal to 0. And around time, we have 0d, we have minus e minus 1 is equal to 0. So we want to solve this set of equations. This gives us in a pretty straightforward, so D equals -1, E equals -1, and F equals, well, okay, this one we have to do a little bit more math. So we have -3 times -1 plus -1 plus F minus 1 equals 0. This is 3 minus 1 plus F minus 1 equals 0. So F equals -1. Okay, so fairly simple equations. Once we solve these, then we have our second dimensionless group. So our second dimensionless group, pi 2, is rho to the -1, velocity to the -1, d to the -1 times mu. Or pi 2 equals mu over rho v d. Okay. The conclusion that we can draw from this is that right, all of these different factors are not, like, drag force is not a function of all of these things kind of willy-nilly. Rather, this group of parameters, which includes drag force, is a function of this other group of parameters. So pi 1 is some function. We don't know what that is after this analysis, but we know that this is true, is some function of pi 2. Or we can say that F drag divided by rho v squared d squared is some unknown function of mu over rho v d. Okay, which is a fairly powerful statement to be able to make. We don't have to measure all of these things independently. We just need to know the right groups of these things, and then we can know how they relate to each other. So F drag doesn't depend on rho v d mu arbitrarily. Rather, it depends through some relation like that. Okay, let's look at what that looks like for a sphere. Okay, so for a sphere, maybe you have heard of the drag coefficient for an object. Probably where most of you would have heard this is like in relation to cars. So sometimes cars are talked about with what's the drag coefficient on a car. We'll do an example looking at that in a little bit, but you can talk about the drag coefficient on a sphere. All the drag coefficient is a slight tweak on just multiplying by a couple constants, a slight tweak on the dimensionless group, the dimensionless drag that we just figured out from Buckingham Pi. Right, instead of the drag force over rho v squared d squared, okay, we take this first part, the rho v squared, we add a 1/2 to make it look a little bit more like kinetic energy type term, a 1/2 rho v squared. We can do that. We can multiply by constants or divide by constants. It doesn't make a difference. And then we do the same thing for Well, instead of d squared, let's just talk about the cross-sectional area. Pi d squared over 4. Okay, again, we're just multiplying by constants. It doesn't change the fundamental relationship. Okay, so on the y-axis, that's what we're looking at. We're looking at our non-dimensional drag force. Then on the x-axis, we're looking at now the Reynolds number, where before we said that the drag force should be a function of, well, it was mu over rho vd, which was 1 over the Reynolds number. So if something is a function of 1 over the Reynolds number, it's also a function of the Reynolds number. So that's no different. So we can flip those ratios. It doesn't make any difference. But the cool thing is the drag coefficient should be a function of only the Reynolds number. So if you look at this data here, you can see it's kind of a weird function. Like it's kind of swoopy and then it does goofy things. So again, we don't know beforehand what the function is. This doesn't tell us anything about that. Like it tells us that if we did 2 wildly different experiments, if the Reynolds number match, the drag coefficient is going to match. So it doesn't matter what experiment we're doing. If we have a Reynolds number right there, our drag coefficient is going to be the same. So if we did an experiment under one set of conditions where the Reynolds number is 5,000, that's going to give us an insight into a different experiment at a different set of conditions where the Reynolds number is also 5,000. So we can match cross experiments. You can see that a little bit in this diagram. The solid dots and the open dots are 2 different experiments. And you can see they all fall on the same curve. So you can see, right, there's a solid dot way down here, solid dots and kind of open circles mixed in together, because all of the data from both of these experiments fall on the same relationship. And you can take a completely different system, as long as it's flow over a sphere, you could use this data to predict what the drag coefficient is going to be for whatever experiment you happen to be doing. So that's the power of similarity, is it gives us a tool to be able to take experiments that are done under one set of conditions and apply them to a model system that's maybe experiencing a different set of conditions. But we can look at transferring those results kind of across like from our model to our real prototype. As long as we can match the right dimensionless groups, then we know like the other dimensionless groups that we care about are also going to match. As long as we can match the Reynolds number, the drag coefficient is going to match. For some experiments, for some systems, it's more complicated than just like a single dimensionless group that needs to match. For example, I'll just show this data briefly, right? There are a whole bunch of other dimensionless groups. We had a handout with all these same guys on it. But if you were, say, looking at drag force on a ship instead of on a sphere in the air, gravity starts to become important. So then you need to not only match, if you wanted to look at a model system versus the real system, you would need to match Reynolds number. You would also need to match the Froude number. And again, if we went through the Buckingham Pi thing, we would come up with that as being the other thing that we need to match. We chose an example where like gravity didn't play any role in our system. This is some data from a test model of a ship. Looking at how the total resistance is a function of both kind of what's happening with viscosity, but also we call the wave resistance, which is related to the Froude number. So first of all, you can see if the Froude number, one of the other things that we said, just to remind us, just kind of looking at the relative values of these different things can actually give us a lot of insight into if it's going to play a role. So we would guess if the Froude number is small, we said that it doesn't matter because that means like that force is not big. We can see that in the data. If the Froude number is fairly small, this is 0. That's 0. So if the Froude number is pretty small, the resistance component that's due to waves is very small, is basically 0. So if the Froude number is really small, we didn't have to care about that. But if it's not small, then we have to care about it. So we can see, right, this is the wave resistance part. This is the viscous resistance part. And then obviously the total resistance is the sum of those two. But if we wanted to take data from a model system and match it to the real system, we would have to, in this case, match both the Reynolds number and the Froude number. And if we did that, then we could match what's happening in our model system to what's happening in the real full-scale system. So some more complicated experiments, it might be more complicated to actually get your model to accurately match what's happening in reality. But it's certainly easier than trying to match all of the different things exactly. It's a way to be able to take a small scale model and use it to understand stuff about a full scale system. Okay, so again, just to lay this out in a little bit more detail in your notes. If we want to look at similarity and model systems, which again are the motivation for doing model systems like that is because a lot of times fluids are really hard and can be accurate to predict the behavior. So we're often going to be looking at experiments on model systems and full-scale systems and trying to develop model systems to do experiments to predict what's going to happen in a full-scale system. Because often we get better information with that, especially with weird effects, than we would if we just ran calculations on something. So our goal for any model, system that we're going to do, we want our model system to scale to our full size system. Okay, so again, that may be obvious. But what we mean by that in kind of this context, we want it to scale up like forces, so that if we measure a force in our model, that force will scale up into the real system. Like a moment, if there's a moment that's happening in our model system that should scale up into the real system. Dynamic loads, right? Anything like that you might be interested in, we should be able to get insight from our model system into what that same thing is going to be looking like in the real system. So, right, it's kind of the next level of like, this is a 1/10 scale model. It's like the forces in the moments and the dynamic loads and stuff are going to scale from what we're observing in our model to what we would be observing in the full scale system. So we can measure the moment, we can measure a dynamic load on some scale model system and be able to scale that up into what's going to be happening in our full size system. So it can give us if you can do it right, it can give you a ton of information on what's happening in the real full size system. To do this, we need kind of 3 levels of similarity. And the first 2 are kind of the obvious ones, and the last one is the hardest one to get. Not always. Number one is actually sometimes pretty hard. The first thing is geometric similarity. Right, so for geometric similarity, we need all dimensions to scale. So if you're making, say, a 1 to 10 scale model, a 1/10 scale model, all the dimensions need to scale the same. Your model system needs to look like the real system does. Right? You can't get really any useful information if your model doesn't look like the real thing. This can be challenging because this can extend all the way down to things like surface roughness. Right? We saw in that experiment with like the two almost identical balls where one was a little bit rough and the other wasn't, that sometimes even small changes like a little bit of extra surface roughness can have cascading effects and can change what's happening. So geometric similarity is not always straightforward, but at least conceptually, it's pretty straightforward. Like they need to look the same, right? So you can't get any information from a real ostrich. Doesn't equal a model pigeon. There's not a whole lot you can learn about flight of an ostrich if what you're looking at is a pigeon. So even if they're like, if it's kind of the same, like that's not good enough. They need to be the same for you to actually be able to gain insight with that model system. Geometrically, they need to be the same. Okay. The second one, again, I think this is fairly intuitive. Kinematic similarity. So kinematic similarity, the fluid velocities just differ by a scale factor. So geometric similarity, the shape, whatever it is you're looking at, is just a scale representation. And the same thing with kinematic similarity, the fluid velocities have to be just different by a scale factor. Right? You're not going to be getting a whole lot of information on this system, like a boat in a river or a sailboat floating in the lake. You're not going to get a whole lot of information about that if what you're looking at is a boat under a waterfall. So if the flow is totally different, like, sorry, there's not a whole lot that you can do. You got to look at two flows that are, again, that are similar, kinematic similarity. Okay, so those are kind of the easy ones. The note on kinematic similarity that I'll make is this also pertains to things like cavitation, or compressibility. So if you're not going to be having cavitation effects in your real system, then you can't have them in your model system, and vice versa. Like you have to have the same physics happening. And same with compressibility. But compressibility is density changes with because of velocity, which happen at some fraction of the speed of sound. So you're not going to get information, you're not going to get useful information on, say, the physics of your airplane at Mach 1 if you're doing stuff on a model system that's at like 25 miles per hour. because the physics are fundamentally different. So you have to match really as the physics of the flow, which I think is straightforward, but it's not always easy to do in practice. Then the last step or last level of similarity that you need is dynamic similarity. Okay, so geometric, kinematic, dynamic similarity. So if you have dynamic similarity, then the forces on the object differ by a scale factor, by a constant magnitude, which that's the really powerful, that's what you're going for in a model system. So you wanted to look, okay, so say you have some object that you're looking at, like in the aerodynamics of it. You want to be able to see in your model system, okay, like halfway down is where we see the transition from laminar to turbulent flow, and that causes, blah, blah, blah. Well, if you see that in your model, you'll see the same thing happening in your real system, where halfway down the object, that's where you'll get, at the same location, that's where you'll get the transition from laminar to turbulent flow. If you're looking at your model object and your drag force is 10 newtons, you'll be able to scale that up and figure out what your drag force would be on your full-size, full-scale object. So that's really the kind of where the goal is for a model system like this, is when you can reach dynamic similarity, because then you can really start to talk about forces and moments and dynamic loads, and anything that you want to be able to measure on your real system, you can just measure it on your model system, scale it up, and there you go. You're off to the races. To get this requires that the key dimensionless groups are equal. And I'll underline that. Okay, so it requires that these dimensionless groups are equal. Also requires the other two. So it also requires geometric and kinematic. Okay, so geometric similarity, kinematic similarity, those are necessary but not sufficient. You need both of those, and you also need the dimensionless groups to match. But if you can get all of that to happen in your model system, you can directly translate whatever you want to measure in your model system to whatever you might want to know about your full-scale system, which I think it's a really powerful experimental analysis tool to be able to do that. We're going to look just here in the next couple minutes. We'll start to set up a problem that will continue on Friday, because we don't have class on Wednesday, which is kind of exciting. We're going to look at how you could figure out drag force on a model, or on a model bus, how you could use that to interpret what's going to be happening on a full-scale bus. So we'll just get started on that and pick that up on Friday. So we'll look at this example. So drag on a bus. So we have a model of a bus. This is what our bus looks like. we're going to put our model bus into a wind tunnel. We made our model so that it was 1/16th scale, so that all of the dimensions scale by a factor of 16. I think that's what I have. Is that what I have written down? Yeah, 1/16 scale. And we're putting that inside of a wind tunnel. And we want to measure, we want to understand what's going to be happening for the drag force on that real full-size bus, because that has a huge impact on what the fuel economy of the bus is going to be, right? How much drag is it experiencing as it's driving down the highway? So we have experimental measurements that we were able to take. We put our bus inside of a wind tunnel, and we measured two things. We measured the speed of the wind, the airspeed, and we measured the drag on the bus. Right, so there's going to be some sort of force meter that's attached to the bus, and it's going to measure, how hard is the wind pushing against the bus. So we have airspeed and drag force. So these are measurements that are done on the model. We haven't scaled this up to our full-size bus yet. We're going to measure the airspeed. These will be in units of meters per second. The drag force is going to be in units of newtons. So we brought this to our wind tunnel, hooked it up, did a bunch of measurements, and here's what our data is. So at 18.0 meters per second, our drag force was 3.10 newtons. At 21.8 meters per second, give yourself some space because we have a fair bit of these. 21.8, our drag force was 4.41 newtons. 26.0, our drag force was 6.09. 30.1 meters per second, drag was 7.97. 35.0, we measured drag, is 10.7 newtons. 38.5, we measured 12.9 newtons. And 40.9, almost done, we measured 14.7 newtons. 44.1 meters per second, 16.9 newtons. And 46.7 meters per second, we measured 18.9 newtons. So we measured drag force, right? Meters per second to miles per hour. It's about a meter per second is about 2.2 miles per hour. So you can see we went up like over 100 miles per hour, so faster than a real bus would go. But we're going to try to use this data to interpret what's going to be happening in our real full-scale bus. And we'll look at, we want to look at the drag force. In this case, we'll look at the drag coefficient. Which is F drag for 1/2 rho V squared A, which is like the frontal area of the bus. Again, this jives with what we found from Buckingham Pi theorem. as a function of Reynolds number, which is rho v L over mu, which again is the other, if we went and did the Buckingham Pi theory analysis, it tells us that this group of variables, the drag coefficient, should be dependent only on Reynolds number. So next time we'll pick this up and we'll actually go through and do the analysis. For now, we will take a break. And we look forward to seeing you guys next on Friday. Hope you get a chance to sleep in Wednesday a little bit.
Thanks. Yep, bye.